when we have to separate radionuclides from irradiated target, usually we use several main methods of analytical chemistry. Maybe the first one, maybe most important, is liquid extraction. Also, we use ion exchange chromatography, extraction chromatography, and some other methods like precipitation or co-precipitation, and sometimes distillating methods. It depends on task which you have to solve. Maybe oldest methods of chemical separation is co-precipitation. It's very typical, for instance, in the chemical analysis of environmental samples and other samples, but it's not so common in separation of radionuclides from irradiated targets, but in some cases we also can use this method with good results. Here you can see some examples of application of precipitation or precipitation. For instance, first one is precipitation of barium nitrates while separating radioactive isotopes of lanthanum from irradiated barium targets. Because maybe, as you know, barium nitrate is not soluble in nitric acid, and therefore it's possible to separate matrix from tracer amounts of radioisotopes. Another example is separation of matrix of silver when you irradiate silver target to produce, for instance, cadmium radioisotopes. It's possible to precipitate silver chloride and cadmium, radioactive cadmium mainly remains in solution. Also, it's possible to separate europium when you irradiate europium targets, for instance, you produce terbium radioactive isotopes, because europium, like for instance, barium or lead, forms insoluble sulfate in redox form of equivalent form. Sometimes, in all these cases, as you can see, we precipitate material of matrix, of bulk material of types. But sometimes it's maybe a good option to separate radioactive isotopes by co-precipitation, for instance, with ferrous ferric oxide or ferrous oxide is create no differences. Both possibilities are available. It's possible, for instance, to precipitate bismuth 207 when separated from lead target. Sometimes it's possible to separate radionuclides by distillation. For instance, interesting possibility is separation of ruthenium as oxide because it's volatile. It's very easy to separate ruthenium tetroxide. Some elements, for instance, selenium or arsenicum, may be separated as halogenides, for instance, from bromides in bromide and chloride form. Halogens may be separated as elements because they are volatile. For instance, here you can see a setup for separation of astatine from irradiated bismuth nuggets that we used in Moscow State University for separation of astatine. Here you can see the heater, and inside this heater you can see quartz tube with small amount of irradiated bismuth, and in airflow it's possible to separate astatine at temperature about 700 degrees, and astatine may be condensed in Teflon capillary in very low temperature, about minus 70, minus 80 degrees. But these methods are not typical for separation of radionuclides. Most important methods are techniques of wet chemistry. For instance, such methods like liquid extraction and chromatographical methods. Liquid extraction is a very common technique of radiochemical separation. In this method, we use distribution of components between two invisible liquids. Usually one of phase is water phase, and another phase is non-polar organic solvent. Typical system. When we separate elements by liquid extraction, we usually use several ligands that form complex compound with metal, and it allows us to separate one element from each other. In order to predict possibility of formation complex, we usually use some theory. It's a theory of hard and soft acid and bases, as you know. The main idea is that hard cations form strong complexes with hard anions, and therefore you can see that, for instance, rare earth elements will form easily form compounds with nitrogen or oxygen containing ligands, for instance, such as nitrate sometimes, or phosphororganic compounds, or others. For soft metals, it is better to use sulfur containing compounds because the complexes are most stable. Another very important method of radiochemical separation of radionuclides is different chromatography techniques. Here you can see the portrait of Mikhail Zret. He was a Russian scientist. He was the inventor of chromatography. Here is very simple, typical setup that we use in our laboratory to separate for column chromatography, to separate from column radionuclides. It's possible to use some ion exchange resins or extraction chromatography resins. It's very easy to do it in laboratory. Here is a typical structure of ion exchange chromatography resin. This is copolymer of sterol and dimethyl. Here you can see the typical structure, and Here is a strong acid cation exchange regime. You can see this sulfonic groups, and this hydrogen may be substituted for another cation, for instance, for metals. Typical structure. This is another option. It's, this is strong base linear exchange regime. For instance, Dalex1, and here is the Dalex50. Here is Dalex1 or some other trademark. Also, some other companies also produced these products by trademarks. Absorption of most chemical elements on cation or anion exchange regimes are investigated in details for many years. I think from the beginning of 50s years of 20th century, and you can see here is a typical absorption curves for different metals. It's easy to find such kind of pictures, and they are very useful for planning of the chemical separation techniques. Here is a distribution coefficient, logarithm of distribution coefficient, and here is molarity of in this picture of hydrochloric acid. You can see, for instance, that for instance, 3 molar or 3 valent elements, for instance, candium may be solved in little conditions, for instance. Here is also radionic exchange, absorption of elements of radionic exchange resin, acid. But typically, usually we use not cationic but anion exchange resin. It's more powerful technique because a lot of elements form anionic complexes in acid media, and therefore we can separate one element from other. If one element forms anionic forms, another doesn't form such complexes. Separate, for instance, you can separate that from bismuth or many other cases. For instance, you can see, for instance, gallium from indium or gallium from zinc, gallium from germanium. A lot of possibilities. Sometimes, usually we make separation in hydrochloric media, but in some cases it's also possible to use nitrate media for ionic exchange separations, but not too much elements for strong anionic complexes. For instance, some actinides form anionic complexes with nitrates. They can be separated from each other. For instance, it's possible to separate thorium from uranium. And also, this is a common method of separation of plutonium from other elements, because plutonium has high distribution coefficients in ionic exchange resin acid media. Also, ion exchange method may be used for separation of lanthanides, and separation of lanthanides is really very difficult problem, especially when you deal with radioactive isotopes, because you have to do this separation with high yield and fast. It's not so easy. Here you can see how ionic radii change depending on atomic number of lanthanides, and also you can see in this picture some other covalent elements. For comparison, for instance, you can see that this is ionic radius for actinium. You can see that it is very different from rare earth elements. And for other actinides, and here you can see ionic radius for scandium and yttrium. It's relatively low. These differences between ionic radius, of course, cause the difference between stability constants of complexes, and therefore we can separate some radioactive elements using some compounds that form complexes with electronides. Here is the most maybe important methods of ion exchange separation of rare earth elements. This is using of cation exchange erasing and eluting lanthanides with alpha halides. Hydroxy is butyric acid. This is the formula of this compound here. As you can see, some rare elements can be separated from each other. But maybe most powerful method of the chemical separation of radioisotopes is the extraction chromatography. We use these methods for many years in our group. We will discuss these methods with details. Here is retention coefficient. It's most important value for planning of the chemical separation. And in fact, retention coefficient is a number of sometimes also known as capacity factor. This is a number of free column volumes that you need to elute your component. It's a number of volume till the maximum of the peak in chromatograph. Of course, it's connected with distribution factor for solvent extraction with the same extract amount. Here is a picture illustrating the principle of extraction chromatography. In this method, we have distribution between two liquid phases. In one water phase, you have your solution of mixture of your elements, and stationary phase also is liquid that is on solvent, on surface of solvent. Solvent is inert, and in fact, distribution is between two liquids. Therefore, the method is extraction chromatography because it's really very close to the solvent extraction, but more powerful than solvent extraction. There are many extractants that were now developed for extraction chromatography. Maybe most typical ones are liquid ion exchangers, for instance, amines and ammonium salts, and also a liquid cation exchanger as, for instance, HDHP. It's phosphoric organic acid. I will show the formula of this compound. And also some solvating and chelating extractants, usually phosphor organic, but not only phosphor organic. For instance, carbamyl phosphinoxide, diglycolamide, phosphate, and other chelating and solvating compounds. Sometimes it's possible to use macrocycles, for instance, crown ethers, and sometimes ionic liquids. Here you can see capacity, typical capacity of solvents, but you have to know that in fact it is not a good idea to separate big masses of radionuclides on column filled with solvents. One of the maybe one of the first one, I think historically the first one resin was true resin that was specially developed for separation of actinides. This is a mixture of tributyl phosphate and carbamyl phosphine oxide or oxide, mixture of these two compounds, and this compound strongly binds both trivalent, especially covalent, tetravalent, but also can retain trivalent actinides. And by this method, it's possible to separate, for instance, trivalent and four-valent actinides. It's a typical way for separation, for instance, of mixture antibody. It's very easy. But in this case, you have to be sure that your plutonium is in fact in tetravalence. You have to adjust oxidation state of plutonium. And here you can see the distribution coefficients of different elements in hydrochloric and nitric acid. And you can see that onto resin, you can see that there is a big difference between, for instance, between strong concentrated acid, for instance, 2-3 molar acid, nitric acid, and between the dissolved acid. Therefore, you can sort a ratio, for instance, from 3 molar acid, and then it may be washed out by dissolved nitric acid, for instance. It's very easy to do it. For instance, if you have 1 milliliter column, in this 1 milliliter column, in this case, you have to use, for instance, 100 milliliters. You can see here 100 milliliters of acid for washing a ratio. Relatively high amount, but it's possible to do. But for plutonium, it's not really possible to wash out tetravalent plutonium from this resin using, for instance, 3 molar acid. It's not possible. It's very high efficiency. Therefore, you have to reduce plutonium, for instance, to trivalent state and then wash out. You can see by the process. It's very easy. The advantage of this method is that, for instance, calcium and iron that typically may present in different sort of samples, they does not affect separation of, for instance, actinides on calcium and iron effects, as you can see. Possible to separate actinides from complex matrices. Another interesting method is to separate, to use liquid anion exchanger. It's ammonium salt. It's similar to WS1, but this is in liquid form, and we can use it for separation some anions on this resin. For instance, we can separate actinides in nitric acid when these actinides form negatively charged complexes. Also, it is possible to separate technetium and platinum from other elements using this method. Here you can see the curves, the dependence of capacity factor from nitric and hydrochloric acid concentration. You can see the tetravalent elements can be retain in relatively strong nitric acid, but they may be washed out with diluted nitric acid or by hydrochloric acid. Also, you can see the expression also may be separated in this. Another very important reagent for separation is DGA, glycolamide. It's extremely strongly binds some trivalent and tetravalent, both trivalent and tetravalent elements, and extremely strong retention of trivalent elements, for instance, beryllium. You can see that here is beryllium, and capacity factor is extremely high. It looks like hundreds of thousands. These methods also may be useful for separation of yttrium for earth elements and for other ones. Here you can see the capacity factors for lantanides, and it means that in fact you can separate in several cases. You can separate neighbor lantanides one from each other. For instance, some iron from Europe, you can see that relatively big difference between these elements. Also, gadolinium from them, for instance. But it is not the case for the separation of hydrogen from mercury or you can see that in this fact, in this situations, it's chemical behavior is very similar. These solvents also may be useful for bismuth, for zirconium, from iron, for instance, in production of iron 55 isotope, or in production of bismuth isotopes. Here is one of the examples of techniques that may be performed using DGA. For instance, it's possible to separate yttrium 90 from strontium 90. It's very easy because of the very pronounced difference between capacity factors of these two elements. It's very easy to do it. Here you can see how it can be done. At first, it may solution may be loaded with 5 molar nitric acid, then strontium may be rinsed with diluted nitric acid, and after yttrium may be washed out by hydrochloric acid. You can see that in 1.0 it's not so high. Also, DGA may be used for separation of radium from actinium. This is very important both for radioanalytical techniques or analysis of experimental samples. It's also important for production of medical radioisotopes, for instance, of actinium, separation of actinium 55 from radium 55, for instance. Here is another interesting example of separation of barium, strontium, and calcium that also may be done using DGA, but it's not very typical task in biochemistry, but it's possible to do it. Another group of commonly used resins is group of LN resins. We have three representatives in this group. The most common and most well studied is LN. LN or LN1 or simply LN. LN is HDHP. This is phosphoorganic acid, and this reagent worked as cationic exchange for solids from another slide. Sorry. But in fact, it here proton in this acid would be substituted for other elements, for instance, for plutonium or trivalent elements, for any hard cation, maybe used for many hard cations. This is similar one, LN2. You can see the absence of oxygen in this position, and this is LN3. And most strong binding is for LN. Less for LN2 and for LS. Here you can see the typical dependence of capacity factors from molarity of nitric acid for earth elements and actinides, and also for divalent elements. You can see that in some cases you can separate rare earth elements from each other, and as for me, resin is maybe most powerful method of separation of radionuclides in production of radioisotopes and in analytical chemistry. You can see that here you can see the difference between these three compounds. This is for LN, for LN2, and for LN3. And this is here you can see ratio of capacity factors to LN1 and to LN2. Sorry. And some other trivalent elements also may be separated using resin. For instance, iron, bismuth, or gallium, and some other elements may be also separated. And then I will tell you about our experience of using this resins group. The first our developed method was separation of actinium-225 from thorium radiated target. We did it together with Dr. Zipov, and I think he will sorry. Here you can see this is a target. It's in graphite cover, I think, and inside is a rubber plate. And here is a spot of accelerator beam of proton beam. We can see here, and this is after the radiation. And during radiation at thorium, we obtain a mixture of many products, because we have not only typical proton-induced reaction, but also fission of thorium, and we obtain all fission products in this mixture. Here you can see the layout of our hot cell chemistry that we organize for hot cell. The first step was, of course, the solution of the target. It's not so easy, in fact, because we need to use a mixture of nitrogen with small addition of fluoric acid, and then thorium material matrix may be extracted by liquid extraction. Because in our target we haven't found maybe 10 grams or more of thorium because of long range of medium energy properties of this material. And by two steps of liquid extraction using HPHP, it's possible to separate thorium, zirconium, niobium, and some other elements. From relatively strong acid in this condition, we some other elements, for instance, rare earth elements, does not they don't extract this condition. And after separation of thorium, it's possible to reconcentrate all trivalent elements, trivalent and remained traces of thorium. It's possible to reconcentrate them on DGAs because of very high capacity factors. And then after we have all trivalent elements on DGA, we can wash out these all trivalent elements, and the thorium remains on traces of thorium. And then it was possible to separate these radionuclides, for instance, using true resin, or also it's possible to use that resin. Here you can see the first separation of first step. Here is the reconcentration of DG. You can see that first of trivalent elements solved on the column, and then they may be washed out using diluted nitric acid. And after we can separate them using tourism. In this article, you can see detailed sources. Our next task was separation of terbium from European targets. We irradiated European by alpha particles and a number of several terbium isotopes, radioisotopes form during this radiation, and also several gadolinium isotopes. And therefore, we have to separate terbium from target material. In this case, we have hundreds of milligrams of target material, and we have to separate terbium from europium. And our idea was to reduce the europium to divalent state, because europium is quite different from other rare earth elements, and this element can exist in divalent form. And we reduced the europium by metallic zinc in hydrochloric acid, and by adding of ammonium sulfate, we precipitate europium as sulfate. And then, after separation of europium sulfate, we use LN resin for separation of traces of europium, gadolinium, and terbium. It was relatively easy. And here you also can see the detailed description of this method. Yesterday I told you about photonuclear reactions, and one of our experiments was formation of lutetium-177 by irradiation of natural carbon dioxide. And here you can see the separation of lutetium from cadmium. It's relatively easy because of a very pronounced difference of these two elements. Therefore, you can here we used resin, also not difficult, was not difficult task for separating these elements. Another application of extraction chromatography is separation, for instance, medical zirconium AG9 from yttrium nuggets, and it's a common method of production of zirconium, the radiation of natural yttrium from by protons or by deuterons, and in our work we have developed separation by different kinds of solvents. As you can see, any of solvents discussed may be used for chemical separation of yttrium and zirconium due to big difference of these two elements. And this picture was taken from PhD thesis of Webster, and here is dependence of capacity factor from mass of metal, and therefore I have to point your attention to the fact that it is sometimes it is really difficult to separate big masses of elements. Even if you separate tens of milligrams, even in this case, capacity factor may drop very significantly. You can see that it drops from hundreds of thousands to 1,000 approximately. Therefore, it is sometimes challenging to separate, for instance, radioactive lutetium from big targets, for instance, from intermediate targets. Yesterday, we discussed methods of production of intermediate. And we, I think you remember that lutetium may be produced by reactor radiation of intermediate. But when you irradiate intermediate in the reactor, you have to produce huge amounts of lutetium. In this case, you have to irradiate at least hundreds of milligrams, but it's better to irradiate maybe grams of enriched intermediate. And in this case, it's really problems that should not solved yet. Separation of small amount of lutetium from such big amounts of intermediate. One example of this method is separation of lutetium from terbium using LN resins that was performed by Horvitz. Was maybe more than 10 years ago. Here is the setup of this separation apparatus, and in any case, it is necessary to use several steps of separation. First step, you have to use a relatively big column, maybe hundreds of grams of sorbent, and in this column you can make some kind of press separation to remove main part of terbium, and then it's possible to make a final separation of a smaller column to obtain pure products. You can see that this method was described in this article, but in fact, it's not so easy to perform. In our laboratory, we also separate radioactive lanthanides. For instance, we produced radioactive thulium by irradiation of ytterbium with gamma rays, and here you can see the difference between two elution profiles. Here resolution of these two elements went we have about 17 layers of titanium in a small, approximately 2 mm column. And here is the separation of the same elements using 2 mm layers. As you can see, it's much better. And therefore, we have to do also 2-step separation. And the first step will separate this part that will, this fraction that will contain approximately 3 milligrams of terbium and most it's described. Also, you can see the separation of 3 lanthanides and 2 terbium on the same resin. We used this method for production of erbium-165. At first, we irradiated erbium by alpha particles and obtained 2 radioisotopes. For instance, 167 and 165, and then it was possible to separate erbium that form from decay of 165. Here is the first step, separation of erbium from erbium and titanium, and this is second one when we separate erbium from thulium. One of the most important radionuclides for nuclear chemistry is copper-67, as I told you yesterday, and there are a lot of problems with production of this radionuclide because lack of production loads. It's not so easy to produce. Maybe one of the most suitable methods of production of copper is irradiation of zinc metal zinc by gamma rays of high energy. That's for nuclear production. And we tried to develop this method in our group, and we irradiated irradiated zinc, with gamma rays, and then we developed a method of separation of copper from zinc. It was really easy because there is a dedicated solvent made by this chem, especially for copper, and use the difference of chemistry of copper and zinc was really easy. And zinc does not retain this material, and therefore it is possible to reprocess big targets, targets of big mass. For instance, we reprocess targets as big as 1 gram approximately on very small column, and it was possible to separate copper from zinc. And this method was described in details articles that was published several years ago in Journal of Analytical Chemistry. And the main idea of my today presentation is that really it is easy to develop a technique of separation of several radionuclides. All you need for development of such technique is close analysis of such distribution coefficients of this like this. You can at first you have to find condition when you will solve when your element of interest is solved and without other impurities. And next step is to washing out this element from your column. In fact, it's relatively easy. The best way is to solve your radioisotope, not the target material. The best condition is if target material goes through column without any interaction. If you have difference between these two elements, it's relatively easy to find such conditions. For in some cases, it's not so easy. For instance, it may be difficult to separate rare earth elements or carbon elements. So sometimes it's not so easy, but usually it's possible to do. I think that's all that I want to say today, and I'm waiting for your questions.
You would please which production route did you use for the patient?
Pollution.
Yes.
We in our group we don't produce lutetium, but as a group in our institution produce lutetium by irradiation of ytterbium with Newton's reactor. But we made some experiments of photonuclear production of lutetium. It was irradiation of natural graphite. But because we have a very small accelerator with very low current, low view current, it was just experiment, not for industrial use. And as we obtained, the yield is relatively low. It's not suitable for this production. I think the best way is radiation of intelligence, but difficult to separate. As I know, I think in Tomsk they developed some methods of separation. There are some liquid extraction methods. Other possibility is to use gas chemistry methods. When you hit the target, there is a very big difference between boiling points of potassium and chemical. Quite different. And in this case, it's possible to separate determinants from potassium remains and determinant distills.
What is the energy of the accelerator?
For photonuclear, 55 MeV. It's not, I think it's not ideal for production. I think for production, we need lower, for instance, maybe 35 or 40 will be optimal for radioisotope production. For potassium, it's not a good idea. It's good for molybdenum, for copper, for styrene.
In copper 67, did you have good yield?
Yes, for copper 67, the yield is better. But of course, in our small machine, we cannot produce large amounts. But if you have good accelerator with high power, of course, it's possible to produce. It will be better than to use accelerators of protons.
But you need high proton energy. There is a problem, or is the current?
For copper, yes, for copper, it is necessary to use medium energy protons. I think maybe 50, 70 MeV, but you have a lot of mixture. You have also copper 64, a lot of much more than 67, and you have to wait till it decays. It also reduces your yield of your protons. It's not best way. But when we use gamma-induced reactions, then I think you are focused without use. Also better.
So gamma-induced reaction is like a promising method.
Yes, and it also applied in the United States for production. They already use this. Let's remember, maybe Moldova and the rest of the world. Other questions? If you have more questions, thank you very much for your attention.
Thank you.
Зачем? Ну, может быть, интересно, там одна девочка заочно выступила, а я не стала. Значит, я скопировал.
ใช่ไหมเนี่ย
So, today, the next two lectures will be given by Professor Boris Zhukov, but unfortunately, after some congress, he is now ill and some, I don't know, else. And he asked to present his lectures. So I will try to do it. I'm not really, it's not my topic, but I will try my best to present his lectures. So we will start with the production of radionuclides by charged particles. That means that we are using accelerators of different design. It can be linear accelerators or cyclotrons to accelerate the charged particles. Mainly today we will speak about the protons, alpha particles, neutrons, and heavy ions, but of course charged particles could be electrons or other particles. And just few words again about the role of radiopharmaceuticals in present world, in our world. So today there are more than 10,000 hospitals already worldwide that are using radionuclides for medical applications, and produce these radionuclides. Nowadays, there is more than 100 different nuclear medical radionuclide producers around the world. And you can see that it is almost 50 million procedures each year that are using radionuclides. So quite a lot of people are treated with these procedures, and you can imagine that the market for these radiopharmaceuticals are quite big, and it is growing every year. In European Union alone, it is around 1,500 nuclear medical centers that are using radionuclides with 10 million procedures each year. And today, if we are looking in literature, we can see that there are quite a lot of new radionuclides. They're not new for physicists, of course, but they're new for doctors, for medical researchers. And these new radionuclides can be applied either for diagnostics or therapy, and this new field of nuclear medicine that is called theranostics, this combination of therapy and diagnostics. And there are some numbers, some forecasts from, as I understood it is from 2014, but I guess it's more or less the same numbers nowadays. So the world market for nuclear medicine, for therapy and for diagnostics is rather big, and it is growing every year. And of course, for therapeutical applications, there are not such a lot of radionuclides nowadays are developed, and that is more important. Not many radionuclides are licensed for therapeutical applications, but for diagnostics, we can use quite a lot of different radionuclides, and all these procedures here, it is mainly diagnostics. And yeah, again, the market is growing, so it's very promising and very perspective. What are radionuclides that are used currently for medical applications? How to remove this? What are the radionuclides that are used currently in the world and or which will be used hopefully in the next decades? So the most important radionuclides is fluorine, that is the molecule with this fluorine 18 fluor desoxyglucose. That is called the molecule of millennia. So because more than, I don't know, 100 million people or something like that were treated with for diagnostic with this molecule for positron emission tomography. A lot of procedures are used this this radionuclide fluorine 18 for PET diagnostics. And one of the another most popular radionuclide is technetium 99M, that is produced from molybdenum 99 in generators. And you can see that this current consumption of these two radionuclides is, I would say, the more than 80%, maybe even more, of all procedures they use these two radionuclides. But other radionuclides, especially gallium and copper, their consumption will increase. And you can see here for therapy, one of the most promising, I would say, radionuclides is actinium-225. That nowadays we can see a lot of papers related to the production, methods of production, and the application of this radionuclide. But not only this, you can see this quite a long list of promising radionuclides. And you can see that in some years the consumption of radionuclides for medical application in USA was increasing. But nowadays the Ministry or Department of Energy is talking about the third wave of medical application of radionuclides, and they make a list of the new radionuclides that will be that some of them are already used in this underlying radionuclides, and some of them will be used in near future, and the demand, the amounts of the radionuclides that are needed will be increasing. You can see these different colors. They are indicated either these radionuclides are used for diagnostics in red, or for therapy in blue color, or some of them have both colors, red and blue. So these radionuclides can be used for theranostics. The radionuclides can be, as you already know, can be produced either by in the nuclear reactors. So it is it can be nuclear reactions with neutrons, or it can be fission products of uranium or usually uranium, of course, and then you purify these radionuclides from the mixture of the fission products. It can it is in the case of yttrium-90, that is a product of the decay of strontium-90, that is a fission product of uranium-235, or it is the case of technetium-99M, that is a product of the decay of the molybdenum-99, that is again a fission product of the uranium-235. If you maybe you heard about this program when the production of molybdenum-99 used not the highly enriched uranium, where radium-235 more than 2%, but they try to use low enriched uranium, low enrichment because of the non-distribution of fissile materials. And again, molybdenum-99 mainly produced by by the extraction from the mixture of fission products for uranium. But nowadays, the production of radionuclides by the accelerators are increasing, and you can see this number of articles every year is increasing. For fluoride, maybe already a peak, because too many applications for fluoride 18, but for other radionuclides, you can see this increase in interest in application and production. There are quite a lot of cyclotrons all over the world, and it is again data, I think maybe 5 or 6 years old, and maybe now it's even more cyclotrons, because new countries are developing nuclear technologies. So I think these numbers can be even higher. And if we are talking not about only research cyclotrons, but also for production of radionuclides, at least in Russia and in many other countries, the need of these cyclotrons is much higher than the current number of cyclotrons. For example, in Russia, we have around 16 cyclotrons that can produce radionuclides, but it is estimated that 1 million of people require at least one cyclotron to produce radionuclides for nuclear medicine. So we need much more cyclotrons than we have currently. And there is some map, some diagram of cities where around the Moscow where we have cyclotrons. Of course, it's not the full list, but the main cyclotrons of centers where the radionuclides can be produced. In Moscow, it is Rosatom Institute in the northeast part of the Moscow, and very close to Rosatom Institute, it is Burnazian Medical Center. So in Rosatom Institute, they can produce radionuclides for radiopharmaceuticals. And in Ogden, we have at least 3 facilities. One of them is Institute for Physics and Power Engineering. Another, this third one, is a cyclotron company, but actually they are located in the same site. And Kharkov Institute of Physical Chemistry, they have nuclear reactors, so they can produce radionuclides from fissile materials, and yes, usually we would have technical tool involved with these facilities in Kharkov Institute and the Institute of not an institute for physics. It will be a tour to the first nuclear power plant in Ogdensk. So this nuclear power plant located on the third level of this Institute for Physics. Troitsk Institute, there Boris Zhukov is working. There is Institute for Nuclear Research. They have a linear accelerator, of proton accelerator, with this range of energies is called middle energy of protons, but for me, as for radiochemists, it's still very high levels of energy, but for physicists, it's in the middle energy. Okay. In Dubna, it's a huge center, Joint Institute for Nuclear Research. It is an international research center where several countries are founders of these institutes. The institute, they have nuclear reactor that is currently, unfortunately, in some reparations, so it's out of order, but for the moment. They have several accelerators, not only protons, but of course heavy ions, and maybe you've heard about them. This institute is responsible, let's say, for production of heavy elements. Aganison was the latest, the heaviest element at the moment was synthesized there, and they have now so-called plant for heavy elements. So it is accelerator with few beams to produce large amounts of heavy elements. Large amounts means not single atoms, but maybe dozens of atoms. Yeah? So for heavy elements, it's a lot of in amount. And in Tver, not far from Moscow, maybe 200 kilometers or something like this, it's Central Institute of Ministry of Defense. And yeah, in the northeast, we have St. Petersburg. There are also several facilities where we can produce radionuclides. What are the stages for the development of accelerator radionuclide production? But honestly, not only accelerator radionuclide production, it's related to any kind of radionuclide, medical radionuclide production. So first, or this list, you can see this order 1, 2, 3, etc. But again, in practice, some of these points we can do them in parallel. So it's not a strong order. You can do some research activities in parallel with other. For example, when we are looking for the specific radionuclide, yeah, when we already choose the radionuclide that we will produce, then in parallel with all this, let's say, nuclear physical researches, we can already do some evaluations of the radiochemical separation and purification of this radionuclide, or we can do some radiopharmaceutical development, because before all this will be done, so all these stages, choice of nuclear reaction, which accelerator we will use, etc., they are needed to produce large or enough amounts of the radionuclides for further application in nuclear medicine. But in parallel, we can look for the best ligands, for the best molecules that will work with these radionuclides. So we don't need to wait physicists when they will produce a huge amount of radionuclides. We can start already with trace amounts and do our chemical research. So, but all these stages, of course, they're important because they will determine the final cost of the radionuclide and the amount that will be available. For example, we can say that this radionuclide, some specific radionuclide, I don't know, even radium-223, that is now used for therapy as a medicine called Sofigo. It is used, you can buy it, but to produce large amounts of radium-223, it's quite a lot of efforts. You can use nuclear reactors, so we use nuclear reactions with neutrons, but you need some starting materials. It can be either radium, natural radium, or it can be some specific thorium targets or whatever. So you need to find the materials for targets, but even when you will find it, you will see that to accumulate to produce enough amount of radium-223, you have to spend, I don't know, years in nuclear reactors with small fluxes. So you need to build or to use the specific nuclear reactors with very dense flux of neutrons. So there are only few such reactors, one in Russia, in Dimitrov, in the Institute of Nuclear Reactors, and some other reactors in Canada and USA. But again, it is a very limited number of facilities where you can produce it. So you, from all the researchers, you see that this radium-223 is very good for therapy, for nuclear therapy, but the amount of this radium that is available now at the market is not so big, it's not enough. So very often all these stages that are dealt with the production of the radium, they're important because again, after these stages, after this research and development, you can say, okay, every year we can produce, I don't know, 1, 2, 10, 100 curie of this radionuclide, and then you can make all these logistic steps where you produce your radionuclide, where you transport it, how fast it should be, etc. And of course, before the application in medical, in medicine, we need this medical trials, preclinical and clinical trial tests, investigations. And only after this step, we can say that, okay, our radiopharmaceutical is working, and we license it, and then all these again, logistic steps are developed. Again, every step here is important for your final business model. Let's say. Here is the classification of this accelerator of charged particles. As I mentioned, for physicists, this range of energies, middle energy, low energy, you can see it started from 15 mega electron volt of the particles. So from 15 to, let's say, 50 mega electron volts, it is low energy accelerators. And you can see this baby cyclotrons with even lower energy of 5 to 20 mega electron volts. And accelerators with higher energy, they are used not very often for production. For some radionuclides they are used, but of course it is mainly used for physical applications, development of physics of elementary particles. And as it was mentioned earlier on Monday by Dr. Ramisa Ali, electron accelerators, they are used for production of photons, and they are used for photonuclear reaction to produce some specific radionuclides by photonuclear reactions. Yeah. What are the advantages and disadvantages of different ranges of this energy? It is not only the cross sections of the reactions, but it also how we can organize the irradiation of our targets. Because when you put a lot of energy to a target, it will be heat, of course, and you need to cool the target. If you have this high energy particles, that means that the energy is high enough to penetrate through even several targets, and you can put these targets not very close to each other, but make some gaps between them. So you can put some water flows between the targets, So you can efficiently cool targets, so it is quite convenient. But at high energies, just imagine that your particles is moving through the targets, and step by step, the energy is decreasing. And if you remember this cross-section plots that Dr. Ali presented on Monday, it was different reactions depending on the energy of the particles. And as far as your energy is decreasing, your reactions, cross-sections are increasing for different reactions. So you will have quite a lot of impurities in your target. So you will produce not only your target radionuclide, but also quite a lot of impurities. But depending on the target radionuclide, sometimes it's quite easy to separate it. For example, you can produce iodine in some solid target. You just need to heat it up, and the iodine will volatilize, and so you can easily separate your iodine from even a mixture of other impurities. But you can see that for high energy, we have low cross sections, and quite expensive, because you need to apply a lot of energy to accelerate these particles. Middle energy protons or particles, they have much higher cross sections. This, as far as it is high cross sections of your target radionuclides, that means that impurities, the cross sections for impurities will be low. I will remind you in this graph. I think there is one in the always the problem. So it's energy of the particles and cross sections, and usually puts something like this. Yeah? And depending on the energy, you will have different cross section and different reactions. So if you have optimal energy and the high cross section of your target radionuclide, it means that cross section and the yield of the impurities will be low. So it's quite easy. But the problem that this middle energy protons or particles, they have not such a huge penetration ability. So there is always a problem with heating of the targets, because you need to put them close to each other to catch all the protons, let's say. But there are some techniques for cooling. And low energy accelerated particles, again, we can get this optimal energy for specific radionuclides. And the cooling, so if we have, for example, beam of the accelerated particles going in this direction from the top, then we can cool our target from the bottom, so it's not really difficult. In this case, as far as the energy is not very high, low energy, the penetration ability even lower, so we can use only one, maybe two targets, and in this case, we can cool the target from another side of the target. Yeah. Here this graph. Okay. As you already know, that for calculating the cross sections, we can use different softwares, and we can calculate or predict the cross sections for different nuclear reactions. But to verify this model, we of course have to perform experiments and to see how our model is fitted to the experimental points. And by obtaining this information, we can modify our model, we can optimize it, and make it better. What are radionuclides? at least for positron emission tomography that can be produced by accelerators. So again, just a reminder that in positron emission tomography we have radionuclides that emits positrons, and then positrons annihilate when react with electrons, and we produce two gamma quanta with the certain energy of 511 kiloelectron volts, that is equal to the mass of one electron. And what is convenient for us that these two gamma quanta, they are going in opposite directions with the angle almost 180 degrees. What are the problem for PET diagnostics is that positron before annihilation have to lose its energy because just imagine that there is nuclear reactions and positron is emitted from the nucleus, and it has quite a huge velocity, and it goes through the matter at high speed, at high velocity, and doesn't react with electrons. So to react efficiently with the electrons, positron should stop, relax, and have the energy that is more or less equal to the energy of thermal movement of the atoms or electrons. So again, positron should stop, let's say, and it requires some time. And during this time, positron goes in some certain direction. So we call it range of the positrons. And that means that if you have your radiopharmaceutical in your tissue, in your organ, and positron emits somewhere here, it goes, I don't know, 2-3 millimeters, depending on the energy of the positron, and it annihilates here. Okay? So we produce the gamma one. So for us, when we see the image, when we analyze the image, we see the place where positron annihilates, but not the place where it was emitted. So that has some not disadvantages, but limitations of PET diagnostics, that the spatial resolution is depends. So spatial resolution depends on the energy of the positrons and on the range of these positrons. So if you have very high energetic positrons, then you have not 2-3 millimeters, but maybe 7 or 10 millimeters. That's why not all the positron emitting radionuclides are suitable for PET diagnostics. The lower the energy of the positrons, the better will be the resolution. But here's the list of the radionuclides that are now already used for positron emission tomography. This or can be used, and already also with 2 radionuclides they are used, but you can see that they are produced not from the accelerators, but from the radionuclide generators. You know about the generators. You have a pair of radionuclides, parental radionuclides, and daughter radionuclides, and you have equilibrium, radioactive equilibrium between them. Either it is transition equilibrium, secular equilibrium, and you can accumulate the daughter radionuclide not for eternity, but for some period of time from the parental radionuclide. So this initial, let's say, radionuclides, they are produced by the accelerators, in accelerators. This strontium 82 and germanium 68, they are produced by the reactions with charged accelerated charged particles. What are the nuclear reactions that are used to produce this main PET radionuclides? It is reactions with low energy accelerated particles, either with neutrons or protons. And you can see that, for example, fluorine 18 mainly produced from the oxygen, or it can be produced from the neon gas, but mainly from oxygen, enriched with the oxygen 18. Other radionuclides can be produced either from nitrogen or from the oxygen 16. And when you produce it in different chemical form, you can use this chemical forms for further chemical reactions. So you can produce either some peptides or proteins with this labeled with this radionuclide, or some other organic molecules labeled with certain radionuclide. What are the cyclotrons that are used for producing the positron emission radionuclides? There is again, the energy range is very low, up to 20, let's say, mega electron volts, and there are some baby cyclotrons that are used directly in hospitals. So you have a full chain of production of the radionuclides, purification of the radionuclides, product synthesis of the radiopharmaceutical, and use it in patient, or it can be some scientific or radiopharmaceutical institutions or producers that use cyclotrons with higher fluxes of this charged particles, means with higher currents. What are the centers, PET centers in Russia? I think some new centers are already there also. So you can see there are not such a lot of centers. So we can 1, 2, 3, 4, 5, 6, something like 20, 25 PET centers in Russia, and earlier I told you that the estimations of the doctors, of the professionals, that we need one PET center for every million of the students. So in Russia we have around 140, 50 millions of people, so we need 140 PET centers, and here you can see that it is only 25, and I guess that's more or less the same picture in many other countries. So what does it mean? It means that again the future of nuclear medicine, let's say, bright, because we need much more these PET centers, and they will be built, and they will require radiopharmaceuticals, radionuclide specialists. So this is quite a promising field of them to work there and to be developed. There is some technical reports by IAEA where they estimate the number of clinical trials worldwide, and the, of course, distribution of these trials all over the world. And you can see it's not surprising the countries where the more cyclotrons are located they have a large number of these files. And our country and say many other Asian countries and African and Latin American countries, they still have low number of trials and not sufficient number of the trials. It is a typical facilities in hospital. It can be located in hospital. So it is a cyclotron for the production of the short-lived isotopes. You can see that the half-life of these radionuclides quite short. So we cannot bring them from I don't know, another system because we will decay and we will have nothing. Maybe except fluorine, but for this very short-lived radionuclides, you have to produce them, purify them, and synthesize your molecule quite fast, and then use it. So you have to analyze it that it is clear and can be used in patients. So all these facilities, all these models, let's say, they can be located directly in the hospital. But if we have either generators where the half-life of the parent radionuclide is rather long, maybe days or weeks or years, we can use generators, or if the half-life of our radionuclide is suitable, we can exclude these facilities in the hospital, so we can exclude radiochemical labs from the hospital. Then it will be much easier all this treatment of the facilities or treatment with radioactive waste, etc., etc. So it is one way, one of the ways to make the life of the doctors easy, let's say. What are the facilities that can produce radionuclides using accelerators in Russia? So as I mentioned already, it is Obninsk facilities. So it is cyclotron company and yeah, there's no type of institute. So it's Kurchatov Institute in Moscow. It is Tomsk Polytechnical University. They have cyclotrons and also nuclear reactor. It is Chlopin Radio Institute in St. Petersburg. So it is the Institute of Ministry of Defense, Troitsk Institute of Research, and some other facilities. So it is some photos from cyclotron company in Obninsk. As I mentioned earlier, they are located at the site of Institute of Physics and engineering. They have two cyclotrons with low energy protons and neutrons, and they produce this number of radionuclides, and also this gallium 68 generator. So the parent of radionuclide is germanium 68, and you can milk the gallium 68 from this generator. And yeah, to work with the irradiated target, they have 7 hot cells. With the low energy protons, we can generate not only this short-lived radionuclides with low masses, like from carbon to fluorine. You can see that we can produce the radionuclides with quite large masses, and they can be used further for PET diagnostics or as for therapeutical use. Here some examples of the production of thallium-101. So it's produced by irradiation of thallium target and then isolation of the lead-201. And when you separate the lead by different methods, you already know about them, either extraction or precipitation or ion exchange. You can see that the half-life of lead 201 is shorter, much shorter than half-life of thallium 201. So that means that all the leads decays, and you have a pure iron 201 that you can use further. Iodine 123 can be produced by several routes. Either we can start with gaseous xenon, and then separate also cesium, for example, or not separate these two intermediate radionuclides waiting before accumulation of enough amount of iodine 123, and then separated either by washing off with some alkaline solution, for example, or it can be some other methods. Or it is irradiation of not gaseous but solid target produced of tellurium. You irradiate it with protons, with split reactions, and of course it is quite easy to separate iodine from tellurium because they have absolutely different chemical behavior, and you can sublimate the iodine from the tellurium dioxide that is used as a target material. Or you can use initial iodine, natural iodine, irradiated to produce xenon, and to produce the iodine 123 with big specific activity, you can separate the xenon simply by, I don't know, airflow or some other inert gas, helium, to flow through the cell, irradiated cell. So you separate the gaseous xenon from the solid iodine target, and then you keep it for some short time, and you produce pure iodine 223 with large specific activity. Again, for medical application, we have to have radionuclides that have large specific activity, either if it is possible without any carriers at all, but if it is not possible, we use as low amount of carriers as possible. And one of the examples for production of germanium 68. Again, germanium 68, just a reminder, it is initial radionuclide for production of gallium 68. So it's a radionuclide generator. So you can separate germanium from gallium target either by extraction or evaporation. It's in the form of tetra fluoride or tetrahydride. Some new medical radionuclides that can be used for therapy or diagnostics or theranostics are listed here. And again, for therapy, I think it was in the first lecture given by Matveyev, where it was quite a simple representation that for therapy we can use particles emitted from the radionuclide and these particles have very short range. It can be alpha particles, or it can be some beta particles with not very high energy. Why? Because due to the short range, it can be several, maybe dozens of microns. All these particles are absorbed by the tissues, and all the energies goes to these tissues. And as far as this energy is rather high, that means that bad cells will be killed by this irradiation. So for therapy, we can use alpha emitters or some beta emitters, but again, by comparison of the range of the particles in the tissue, you can see that alpha emitters are much more preferable for therapy than the beta emitters. Or you can use the Auger emitters, Auger electrons, Auger electron emitters, because Auger electrons they have very low energy, and thus they have very low range in the tissues. To use Auger emitters, you need to apply some specific biological vectors that will deliver your radionuclides specifically to the core of the cells to destroy the DNA and thus kill the cells. So I think there are more than 30 slides. I think that we can stop at this moment, have some lunch, and then continue with this thing. Okay? So, then I will wait you here. So we'll continue this paper. Here is the list of the accelerators, the proton beams of middle energy, the middle energies, and middle energies here it is let's say up to 200 mega electron volt. Here at TRIO facility you can see here 500 mega electron volt. It is already high in energy. But they have option to use 110 mega electron volt proton beams. So there are, it's not a full list, but the list of the facilities that are let's say topic, they produce radionuclides, and at least they're working together, as I know, with the Troitsk Institute also. And here will be some examples of these accelerators. First is facility in Los Alamos National Lab. Usually they, not usually, generally they have this 100 mega electron volts proton beam with this current up to 215 microamperes. And sorry, they have three targets with a distance between each other about 3 centimeters, 32 something millimeters, and due to the energy loss in these targets, they have these 3 energy ranges in each target. So they have different energies in different targets. Also, the beam, as you can see here, the shape of the beam is like a ring, O-ring shape. So they irradiate not the, it's not a, let's say, scanning mode. It's they irradiate only this ring in the middle, or not middle, in the circle in the target, and some calculations of the energy losses in this in these targets. The next one is Brookhaven linear accelerator, built 50 years ago, so still working there. So they have they mainly used for nuclear physics experiments. So the production of the radionuclides is like a big product of the use of the accelerator. So the main users of this accelerator are physicists, nuclear physicists, but again there is a possibility to have beam with different energies from 66 to megaelectron volts, and they can use it. Here it's called parasitic operations. So to produce some radionuclides. Triumph facility in Canada. So it's the full schematic overview of the facility with the initial source of the protons found in the main circle, let's say, in the main accelerator. And they have different beam lines for experiments, and also one beam line for production of radionuclides to irradiate targets and produce radionuclides. The main production there is strontium 82, and strontium 82 is parental radionuclide for rubidium 82 that is used for in PET diagnostics to look for the muscles, for the heart. So because rubidium is an analog of alkaline metals, sodium, potassium. So rubidium is used as an analog for these metals to see the work of the muscles in the body. And strontium 82 can be produced via different routes. Either it is irradiation of natural molybdenum, so there is no need to enrich molybdenum with certain isotope like 98, like for nuclear reactors, for example, or it is irradiation of initially rubidium 85 to produce strontium 82 to produce rubidium 82. So this long chain. Cyclotrons in cyclotron in nuts in France produced by IBA in Belgium. Many cyclotrons in Europe, in Russia, we have one. They are produced either in Belgium or Netherlands. So big companies producing this very complicated facilities. So in this cyclotron, they can use either protons or neutrons or even alpha particles at this middle range energies, and they also have this hot cell facilities as everywhere in production of radionuclides. In Indiana, they have this new cyclotron called Purium. What are the advantages? They have a proton beam, only proton with energy of 70 mega electron volts, and it is fabricated as model. So this commercial cyclotron produced as a for wide applications, so should be not very expensive, but I don't know the for the price for this cyclotron. And again, in cooperation with Institute of Nuclear Research in Troitsk, where Zhukov is working, they developed this technique to produce strontium 82. And one of the important and sensitive part of the radionuclide production is the material of the targets, because if targets are not proper produced, or the material of the target is not suitable for irradiation, you can have this degradation of the target or the shells, and thus you will lose your material. So it's main some facilities. They are main because main in collaboration with Institute of Nuclear Research. So that means the main facilities. So the main facilities with which Troitsk Institute is working for strontium 82 production. And there are some accelerators with high intensity proton beams of the same middle energy up to 200 megaelectron volts. And you can see here in the list all these cyclotrons, and it is proposed. So as I understood, they're under construction or maybe already constructed. I don't know. But you can see that not only in Europe and USA, there's South Africa, some Ukrainian institutes, Russian institutes, quite a lot of accelerators. And now this linear accelerator that is built and that is used in Troitsk, in this Institute of Nuclear Research. So it was constructed in 1992, and the proton energy, the main energy that we use is 158 mega electron volts. But of course, in all these accelerators, you can change this energy. If you put some shielding, let's say, or some materials before your target, so part of the energy will be lost in the shielding, and you can have proton beams in the lower energy. But the maximum energy this. And they are already producing some radionuclides. The problem, not problem, maybe small disadvantage of this facility that it is not constantly working facility, so they turn it on for some operations, not very long in time, and they produce enough amount of the radionuclides for some period of time. And so it is like cyclic working in this facility. Here is the design of the target folder. Here you can see the proton beam is going in this direction, in this beam line. There is a lithium window, so light materials not to absorb a lot of energy. And there are some targets. One of them are used for controlling the proton beam, the energy of the beam, the intensity of the beam, and some targets are used for producing radionuclides. So here is the photo of this target holder, and some examples of the monitor materials, so to see the flux of the protons, the shape of the proton beam. And there is a list of the radionuclides that they produce. Strontium-82, the main radionuclide that they produce regularly. It is produced by irradiation of rubidium target, and I will show it will be interesting example of the proposed system for this production. Also, they can produce this list of radionuclide, so they not produce it for regular sale, but for some customers, they produce several parties of this radionuclide. So if it will be needed, let's say, they can make it regularly. And this list of radionuclides, this radium-223, that is very important for us, and copper, some copper isotopes, they develop the method for production. But the technology, the targets, the method for separation, extraction, separation are still under development. And again, there are some examples of the targets, how they look like. So this is liquid rubidium target. So it's not liquid rubidium that you can see. It's with some shells. Palladium produced from the silver target. Tin is produced from antimony target. The alloy titanium. Germanium-68 is produced from gallium, sodium from aluminium, and actinium-225 from the thorium target, and in this case it is natural thorium target. So, and they sent the isotopes that they produce to different facilities. It is not only Russian facilities, but it is some abroad institutions, mainly in USA, but not only. So this is the line for production of strontium-82. They irradiate target of rubidium in Troitsk, and then they ship it to USA, to Rosatom National Lab, where target is processed. So in USA, they extract strontium-82 from the target and use for medical applications. So during these years, more than 350,000 US people were diagnosed with this rubidium-82 that we milk from strontium-82, and yeah, so it is some estimations that 2 million patients are diagnosed with the other isotopes. So I think it should be some, yeah. I thought it should be some video, but no. There's a modeling of the distribution of temperature during the irradiation of the target. In this case, the model takes into account metallic rubidium, so it is a liquid, and rubidium chloride, that is solid. They investigated the distribution of the temperature, of the doses, and finally, as I understood, they decided that metal rubidium is more suitable for production of strontium 82. And what they can obtain, the yield of strontium 82 is 4.5 millicurie per microampere multiplied by hour. So what they can produce during one irradiation at the end of bombardment, it is about 7 curie of strontium 18. So quite a lot of enough activity for treatment of several, not several dozens of patients. And here is the development of online strontium 82 production that I mentioned earlier. This interesting technique. So what is here? They have this target that is irradiated by photon beam, and there is a constant flow of metallic rubidium through this target. So it's not how to say it, target that you fix, that you remove it and fix again. No, it is a constant flow of the rubidium that is irradiated by photon beam. During irradiation, there is a production of strontium 82 that is dissolved in rubidium, and in hot cell there is absorbance. Either it is some sorbent rods made of cellulite or something, or some metals with high temperature of melting, or it can be some filtration. So rubidium will go further and strontium will be accumulated here. So it can be different design of the strontium separation from rubidium. But you can see that it is constant flow and constant accumulation of strontium-82 without any need to dissolve this target, to separate strontium. So you just take out these sorting rods and you have your strontium. So quite interesting technique. They're still working on it, but I think the idea is very nice. Yeah, this schematic logistic route of the production. They produce rubidium target in Murmansk that is further shipped to Troitsk, where they irradiate with middle energy protons. And then this irradiated target, they don't process this irradiated target directly in Troitsk. They either ship it to the USA, to the Rosatom national lab, where they extract strontium from rubidium targets, or they ship it to Obninsk, to Institute of Physical Energy Institute, where they also process this target, extract strontium-82 and ship it further to St. Petersburg for medical application. They are planning now to create their own chemical lab at in Troitsk at the institute, but again the work is still ongoing. They're shipping it now. And it is a virtual isotope setup, how they call it. So again, the production of isotope here, shipping to USA, and then shipping the generator of rubidium 82 from strontium 82 to other facilities even to South Africa. Another example is the production of tin 117M metastable. So this radionuclide, it is not only a gamma emitter, because all metastable radionuclides, they are gamma emitters. When they go to the from excited state to the ground state, they emit in gamma rays. But also due to the energy conversion, this radionuclide emits some Auger electrons. So I remind you that Auger electrons, it is electrons that emitted from the electronic shells of the atom, not from the nucleus, from the nuclei. And thus, as far as they are going from the electronic shell of the atoms, the energy is not so high as it could be for beta particles, for example. And due to the low energy of these electrons, emitted electrons, they have short range in water, and that means in our tissues also. And thus this radionuclide can be used for therapy, for nuclear therapy. Also, as far as Auger electrons, they have certain energy. It's not like beta particles that have homogeneous spectrum. The full range of the particles emitted by the nucleus from 0 to maximum energy of the beta particles. But Auger electrons, they have some certain energies, values of energy, and thus the ranges are also some certain numbers. To produce tin, they irradiate antimony targets by photons, and there are different reactions, either P2P or P3N or P5N, and but the resulting radionuclides, depending on the isotope, that will be one of the resulting radionuclide will be team 117. And yeah, some examples of the targets. Either it is metallic antibody covered by covered by graphite and by nickel, or it is alloy of titanium and antimony. So different targets can be applied to this technology. There is an example of the theoretical calculations by different software, by different models of the cross section of the reaction of antibody with protons, depending on the energy. And you can see that in some high ranges, again, high for me, so for them it's still middle energy of the protons. There is quite good fitting, quite good agreement between the theoretical and experimental part. And again, after the irradiation during the 5 days, they can produce 3 curie for the target radionuclide. So another example is the production of selenium-72 as a parent radionuclide for arsenic-72. So again, it is an example of the radionuclide generator, long-lived parental radionuclide, short-lived daughter radionuclide. In this case, it is transition equilibrium. And again, modeling of the cross-section of the nuclear reactions, and depending on the target material. Either it is intermetallic compound gallium arsenic, or selenium can be produced by radiation of bromide. So, here we have selenium, and we can go either from arsenic or from bromide. And this is cross-section of these different reactions. And you can use both of them. In both cases, you will obtain more or less comparable yield of the target radionuclide. Next example, it is production of palladium 103, the main radionuclide that we would like to obtain by the irrigation of silver targets. And you can see, fortunately, that the cross section of the production of palladium 103 is much higher than the cross section for palladium 100. So again, by choosing the correct energy of the protons, in this case it is 70 megaelectron volts, you can produce with high yield your target radionuclide and minimize at the same time the production of the end product. And after the processing time is 13 days. Again, it was necessary to decay the palladium 100. So after 1 month, the total produced amount of palladium 130 was 23 curie. But the purity, even if the quantity was lower 2 times, but the purity was much better. So less than 0.1% of palladium 100 was in this material. So one of the very promising radionuclide is for therapy is actinium 225. it can be produced by different routes, and one of the routes is the irradiation of natural thorium target with protons of middle energy. It is quite convenient. Thorium is not very expensive material, and there are a lot of thorium. So you can easily have the material for irradiation, and the cross sections are also quite good, at least at high energies of protons, more than, let's say, 100, 150 megaelectron volts. So you can obtain quite a lot of actinium by irradiation of this thorium target. Why it is so interesting for application? Because actinium and all its daughter radionuclides have quite short half-life, and there are 1, 2, 3, 4 alpha particles emitted from, let's say, single actinium. So it's quite a huge amount of energy that will be transported to the tissue. So actinium 225 is very efficient to kill the cancer cells, for example, and you can see that all these half-lives are very short. That means that if actinium comes to the target tissue or organ, all the alpha particles will be accumulated, will be transferred to these bad cells, and no radionuclide will be spread to the other parts of the body. So it's quite interesting, quite promising, and that's why there are quite a lot of efforts to obtain pure actinium-225. Why pure actinium-225? Because one of the impurity during the irradiation of thorium is actinium-227, and this radionuclide has very long half-life. So that means that if there will be a lot of actinium-227, it will be in your body or in the body of the patient for very long time. So if actinium-225 will decay, let's say in 3 months, then actinium-227 will be more or less for the rest of your life. Not very good. So one of the main radionuclide to control in actinium-225 is actinium-227. Another interesting radionuclide is protactinium 230, because it can be used for production of uranium 230 that also has comparable with actinium-225 half-life, and also have 1, 2, 3, 4, even 5 alpha decays in its decay chain. So again, and all the daughter radionuclide have a very short half-life, maybe only lead-210 has very long half-life, but in this case, the amount of lead-210 will be very low because the difference of the half-life. So it is 300 times longer half-life, so the amount will be 300 times lower of lead-210. To irradiate thorium, different designs of the targets was tested. One of them is the so it's thorium metallic thorium oil inside the either graphite shell or covered by neodymium. And so there's an example of this targets after irradiation. And one of the most difficult part of the production of actinium-225 is the separation of actinium-225 from the products of the irradiation, because thorium, irradiated thorium produces around 30 elements, and you have to extract only one of them, only actinium. And another problem that even if the yield, the cross section is high enough, the amount of actinium in thorium target is variable. So it's around, I don't know, less than 0.1 mass percent of thorium. And if you remember all these separation methods that were discussed today and yesterday, they use some specific extractants or sorbents, and thorium, as far as it has the charge, thorium is +4, and actinium has the charge +3. Thorium will be much easier contact with all these extractants due to the higher charge. And to separate actinium from thorium, the small amount of actinium from a huge amount of thorium can be changed. So the first step of this separation is the extraction of all the thorium. So it is removal of the main bulk mass of thorium, and then in water solution you will have some minor amount of thorium and actinium in more or less comparable amount concentrations, and then you can use this extraction chromatography and other techniques to separate them. But first step should be the isolation, the separation of the huge amount of thorium. And there's some prediction of how much actinium-225 we can produce by irradiation of natural thorium targets with different proton energies at different facilities, at different currents, but current more or less the same. On the aromax it's larger, but the proton energy is lower. The yield will be not so good. So there is again this depends. The higher the proton energy, the higher the cross section of the reaction. So here we can see this from this estimation that the more energy we have of the protons, the more actinium-225 we will produce. And this trium facility, they have 500. So as I mentioned, they have maximum energy of 500 megaelectron volts, but they have also option to irradiate targets at 110 megaelectron volts. But it seems not very reasonable to use this energy. So it will be interesting to see how much actinium-225 they can produce in Canada at this facility. And there's some summary of the possibility of medical radionuclide production at Troitz, in Troitz at the Institute of Nuclear Research again. So they have this strontium 82 for production for generators of rubidium 82 and all these other radionuclides. So what we can see here, that they currently have linear accelerator. So it is estimation of how much QE they can produce of these radionuclides and how many patients can be treated with this amount of produced radionuclides. So quite a lot of doses procedures can be done with, and again, it is production of only at one facility. And there is some estimation for new cyclotron that they are planning to construct, and in this case, it will be even higher annual production of the radionuclides, because much more patients can be treated in the future. So, and there's some statement from Boris Zhukov how to solve or the problems that need to be solved in research and development for medical radionuclide production, maybe not only in Russia, but in other countries. So the first is to overcome various in the disposition of funds for research and developments. I think it's one of the main problems everywhere. In Russia, we have this problematic barriers because the funding usually come at the end of the year, and you should work the full year without this funding, and on the end you will get it. So some strange disposition of funds in Russian Federation, not for all funding organization, I would say. Some funding operation funding agencies have this possibility to send money at the beginning of the contract, but it's not not always the option. So next, to provide sufficient governmental funding again to establish new facilities or upgrade the existing facilities. As we've seen from this slides, one of the, at least in Troysk, this accelerator was built already more than 30 years ago. Of course, facility is degrading, aging, and we need to either build new facilities or upgrade the old facilities, but it requires a lot of money. Even usual analytical techniques, I think in this cyclotrons, they cost quite a lot of money. And these accelerators, I don't want to think about how expensive are they. To form a qualified and independent international committee for distribution of funds to create and realize isotope projects. So here, it is not only about the construction of the facility or upgrading, but also funding of the cooperation efforts to realize the project, because these logistic systems, they also, everything costs money, and it's not only production but also this transportation system, licensing, and the consequence of this point is the need to improve the logistic systems. Yeah, the next is to reduce bureaucratic regulations without prejudice to safety and security, of course, but that means the number of papers that we need to write for any kind of work with radioactive materials, with these licenses, with this transportation, with buying radionuclides or selling them, etc. And of course, to educate the highly qualified specialists in this field, in the field of radiochemistry, in the field of medical physics, nuclear physics, radiochemistry, and so forth. I guess it is, yeah, it is the last slide for this presentation from Boris Zhukov. Unfortunately, I don't have at the moment his second presentation, but he said that he will send it maybe at the end of the school, so you will have the presentation on the topic of high temperature. So now we have some time, maybe 15, 20 minutes before the exercises in labs. So we can let's complete. So then we will continue. Thank you.